Good morning. Today is Monday, March the 30th, and today we are going to talk about section 10.6, which deals with using the law of conservation of energy. Now, earlier in this chapter, we talked about what the law of conservation of energy was, right? The total energy of an isolated system beforehand must equal the total energy of that isolated system afterwards. But now, if we're dealing with a system that's not isolated, that means that there's a change in energy somewhere. And so the final total energy and the initial total energy are not going to be the same. How do those things vary? Well, the initial total energy plus the amount of work that's done on the system equals the final amount of energy. So let's look at that. All right. So we can use the law of conservation of energy to develop a before and after perspective for energy conservation. So, excuse me, if you look at the formula for work, which is shown on this line here, the total amount of work done on a system is equal to the changes in each of those individual forms of energy. That means that the initial energies plus the amount of work is going to equal the final energies plus any heat that might be lost due to the force of friction. And so this is the same type of equation that we dealt with when we were talking about the law of conservation of momentum. Now, in an isolated system, we know, of course, that the total work is equal to zero, so we can ignore that work aspect on the right side of the equation. But in reality, work is almost always done, and so therefore that's an uncommon kind of situation. So, however, let's talk about isolated systems and start there, and then we'll move on to systems where energy is being put into or taken out of the scenario. So an isolated system, a good example of a real isolated system is gravity, right? An object that is in free fall, all right? If an object is falling near the surface of the Earth, it will accelerate from its highest location to its lowest point. And if we ignore air resistance, which we can do for small distances, then this is an isolated system. An object sliding down a frictionless ramp. All right. Now, in reality, most ramps are not frictionless, so that's not a terribly real scenario. An object compressing a spring. We know also that we're going to change the internal energy as we squeeze those molecules together. We're going to change the internal energy, but we can talk about it as an isolated system. And then finally, an object sliding on a surface without friction. Again, not really an accurate depiction or idea. But let's look at an example of this and see if we can do some calculations. So the example here starts with a kid on a water slide. So while at the county fair, Katie tries the water slide, whose shape is shown in the figure. The starting point is 9 meters above the ground. She pushes off with an initial speed of 2.0 meters per second. If the slide is frictionless, how fast will Katie be traveling at the end of the slide, or at the bottom here? So what we have to realize is that up here, she's got some kind of gravitational potential energy, all right, whatever, based on her height above the ground. And that gravitational potential energy is going to be based on the 9-meter deal. She also is initially in motion at 2 meters per second, and so therefore there is kinetic energy at the top. At the bottom, on the other hand, the height above the ground is now 0. So, and we're looking for her final velocity. So the way that we set this up is by using the law of conservation of energy. The table showed that the system consisting of Katie and the Earth is isolated because the normal force of the slide is perpendicular to Katie's motion. and does no work. If we assume, right, because the normal force is up and down, right, opposite of gravity, but she's moving toward the right. So if we assume that the slide is frictionless, we can use the law of conservation of mechanical energy. And so the final kinetic plus the final gravitational potential is equal to the initial kinetic plus the initial potential. Now, we know that the final, I'm starting to get annoyed. The final, what the blazes? The final gravitational potential energy is 0 because she's at the ground. So we need to, we're going to use the final kinetic and set that equivalent to the initial kinetic plus the initial potential. Now, if, so therefore, that's what we show here. If I rearrange this algebraically, first things first, get rid of the masses. Okay, they go bye-bye because there's a mass on each side. And then multiply both sides by 2. Then take the square root of both sides. I end up with the formula VF equals the square root of VI squared plus 2 times G, the initial height. Plug and chug, and I end up with the square root of the quantity 2 squared plus 2 times 9.8 times 9, and that gives me approximately 13 meters per second. So when Katie gets to the bottom of the slide, she's going to be moving horizontally at 13 meters per second. And again, as we talked about in the previous section, the shape of the slide doesn't matter. It's just the change in her height above the ground. Okay. All right. Another example. Monica pulls her daughter Jessie in a bike trailer. The trailer and Jessie together have a mass of 25 kilograms. Monica starts up a 100-meter long slope that's 4 meters high. On the slope, Monica's bike pulls on the trailer with a constant force of 8 newtons. They start out at the bottom of the slope with a speed of 5.3 meters per second. What is their speed at the top of the slope? Okay, so we've got gravitational potential energy. We've got initial and final kinetic energies, and we are obviously doing work on this trailer, okay, because she's pulling it. She's applying a force and carrying it through a 100-meter long slope. So let's make ourselves a diagram and a laundry list. All right, so here's the diagram. We've got the woman on the bicycle pulling the kid in the trailer. All right, and she's going up. This is a 100-meter long slope. That's D. And this is the height here, which is 4 meters. Okay, so we have an initial height, which is 0, an initial velocity, which is 5.3. We know that the mass is 25 kilograms, the force is 8 newtons, the displacement up the slope is 100 meters, and we know that the final height is 4 meters. And here is our big fat question mark. We're looking for the final velocity of the bike system here. We set this up using the law of conservation of momentum. The final kinetic energy plus the final gravitational potential energy is going to equal the initial kinetic energy plus the initial gravitational potential energy plus the amount of work that she does. We know that the initial gravitational potential energy is going to be 0, so we can get rid of that. And
it's
then
9 o'clock.
Well, thank you, Jesus. Then we rearrange the equation. So we already got rid of the initial gravitational potential energy because the initial height is 0. We know that the work is equal to force times displacement. And then doing the same thing we did in the last equation, getting rid of the terms for mass, multiplying both sides by 2 to get rid of the 1/2, and then solving for the VF squared formula, we get VI squared minus 2 times G times the final velocity, or final height rather, plus the work divided by mass, right? We divided both sides by mass, multiply both sides by 2. We end up with 5.3 squared minus 2 times 9.8 times 4 plus 2 times 8 times 100 divided by 25 kilograms. Do the math there, and you end up with 13.7 meters squared per second squared. But remember, we still have to take the square root because it was VF squared. The square root of 13.7 is approximately 3.7 meters per second. All right. So in this particular case, she has slowed down from an initial velocity of 5.3 meters per second to a final velocity of 3.7 meters per second, even though she was doing work to move up the slope. Okay. And think about that. If you ride your bicycle up a hill, generally speaking, you're going to be moving slower when you get to the top than you are at the bottom. Okay. So that brings us to our discussion here. We have a homework assignment due on section 10.6. Homework questions 28 through 40, odd numbers only. All right. Gentlemen, have yourselves a happy Monday, and I will see you tomorrow.